Okay, good morning and welcome to you all to this course on embedded systems. We will try to understand in today's lecture, which is the first lecture, how embedded systems differ or how embedded system poses some additional constraints over the other general purpose systems that we have encountered in our learning process till now. Now, embedded system, what is an embedded system? If we ask this question, what is an embedded system? The possible answer is an embedded system is a system where a microcontroller based or microprocessor based programmable system is embedded in a larger system. So, we will have a larger system which can be this is the larger system in which there is a microcontroller based or programmable system embedded. Always it may not be programmable, by the way, it may be also hardware programmed. Okay. So, there is some processor embedded inside this and which interacts with this larger system at different levels. So, this system actually takes inputs from the world, and by the world I mean this environment to be the world for this embedded system. So, it takes inputs from this world, processes the information, sends it back to the world. It can come from different points of this larger system, and the after computation the responses can go to again different points of this system. The points which are affected, because you see the larger system can have many things, everything may not be controlled by the embedded system, everything may not be sensed by the embedded system. So, the parts which are sensed, acted upon and actuated upon are often known as the sphere of control. So, might be there is a sphere of control around this embedded system within this larger system that is being affected by this embedded system. All right. Now, typical examples of embedded systems. Now, you can think of embedded systems are everywhere. You can say, if you take your mobile phone, it has got many communication systems, but also there are processors. Even earlier, if you take the printer, inkjet printers or color printers, there also the controllers are there. Even if I go even earlier, there are some disk systems where intelligent controls are embedded. Okay. Printers I have already said. So, systems have been embedded inside larger systems for longer time. Nowadays, we find intelligent washing machines, where depending on the volume of the clothes, the extent of dirt in the clothes, the gyration, the speed at which there will be centrifuged or how much detergents will be required, all are controlled automatically. How is it controlled automatically? Using some embedded systems. Again, if we go to more advanced things, now most of the modern cars are coming with not one embedded system, but multiple embedded systems, okay, which some are taking care of controlling the brakes, some are taking care of the cruise control, some are taking care of the locking system. So, there are a number of embedded systems impregnated inside the larger system, that is the car. If we look at the airplanes, most of the airplanes now are said to be not so much dependent on the pilots, right. So, there is a set of embedded controllers inside that, which can negotiate with the environment, okay, and those are also embedded systems. In warfare, when we find the when we want to have some rocket launchers, there also embedded systems are there which are taking signals from here. So, the list gradually becomes endless nowadays. Now, if we look at, now this is also known as sometimes a variant of such embedded systems are known as cyber physical systems. This term is becoming popular day by day, where the cyber part means the computer interacting with a physical environment. So, the physical environment can be a road on which a car is moving, right. The road will have different frictions at different points, that is the physical reality. And now, I have got a car which has got a controller which will keep the speed fixed at a particular set level. Now, from your school level knowledge of physics, you know that in order to keep the speed constant, when the friction increases, you have to apply more force, and the reverse when the friction goes down, in order to keep the same speed. Now, that the physical reality is the road, the physical reality is the condition of the tires of the car, and the controller is within the car. This is one sort of thing, one sort example of cyber physical system. This can be further extended nowadays to the term which many of you have heard, which is Internet of Things, IoT as it is told. IoT is nothing but a set of systems spread around, may be distant. Each of them have got their embedded controllers, embedded sensors, everything, and they are communicating over the internet, and one system can communicate and actuate another one at a distance. Therefore, everything gets connected through the communication of a set of embedded systems. Okay. Now, coming back to embedded systems proper, if we think of an embedded system, it will consist of say a microcontroller based system or processing system. Let me call it the processing system, which usually are microcontroller or microprocessor based if they are programmable. And on the other side, we have got the sensors, which interacts with the world and provides the data to the processing unit, and there are actuators. Okay. Actuators. Now, these actuators are actually affecting the physical world or the larger system. Let me call it the other system, whatever that other system might be. All right. And the sensor is sensing some variables from this other system and feeding it to the processing unit, and depending on whatever actions are to be taken, they are the actuator is actuating it. Now, in between I have missed out certain things intentionally, that is, it can, the sensors are sensing the data which are coming from the other system, which is the physical world, which is mostly analog, all right, mostly analog. Right, if it be an analog system. Therefore, there can be two things. The sensor can directly sense the data in the digital form. Otherwise, if it does not do that, then here we need a layer of interface, which is the analog to digital converter, because this processing system is a digital machine. Similarly, we have to give the data to the physical environment mostly analog, may or may not be, but if it be an analog system, then we need here a D2A converter, digital to analog converter, right. Now, often the actuators can be direct digital and can provide the control, that we will see some examples later, all right. So, this is the overall environment. So, in order to learn embedded systems, we have to learn we have to have some knowledge about the sensors, what sensors, how do we specify sensors. Maybe many of you know how analog to digital converters or digital to analog converters are working. We will try to brush upon that again. And most important part is this processing unit, where we will see that different types of processings can be involved. Now, one can ask the question that in a typical architecture of a computer system, we also have got the input device, the CPU and the memory, the processing device, processing block, and the output device. So, where does it differ from a general purpose system? So, how does it differ from the general purpose system? So, general purpose system versus embedded systems. Usually, the embedded systems are one embedded system is for one purpose. So, single purpose, okay, or single application. That is point number 1. The other point is the embedded systems is severely, usually what happens here, what do you mean by this? A single application program is repeatedly run whenever for a particular, say for example, let me give the example of an answering machine, telephone answering machine. It has got a fixed task that when the call will come after 5 or 7 rings, if the receiver is not picked up, see all these things are to be sensed that the receiver has not been picked up, then the answering machine goes on. After a delay plays a message and gives a beep. After recording for a particular delay, it cuts it off, all those things. Now, this is a fixed program. It has been written once and have been put in an embedded processor, which has been put in the answering machine or the telephone system. So, that program is repeatedly working. The other option is, other distinguishing feature is, it is very tightly constrained compared to the general purpose system is not single purpose, it will be multiple purpose. It can be used for different purpose. Now, is tightly constrained in terms of what? It must be low cost. The cost cannot be exorbitant like a general purpose server, right. It should be low power. Mostly we would like to run this on battery. It should be portable. Okay. It should be sometimes it must be real time. In general, it should be fast. It should be fast all the time, but sometimes it should be hard real time. I will come to that, what it means. Okay. So, these are some of the constraints that are specific to embedded systems, but not so much for general purpose systems. On the other hand, general purpose systems are more powerful in the sense that it can do many more things. It is not single purpose, it is not constrained by these things, it consumes more power, usually runs from the direct electric supply with some battery backups and all those. So, that is the differentiation between general purpose systems and embedded systems. Most important thing is it is predefined. What I am going to run on an embedded system is predefined application. In some cases, you will find that multiple applications are running on an embedded system, but those are also predefined, 3 or 4. It cannot be just like a general purpose system that you can go on adding to this, right. I will differentiate between another thing, that since right now I have said real time systems, let me also differentiate between RTS and embedded systems. What are real time systems? Real time systems are systems, it can be of two types, hard real time systems and soft real time systems. Hard RTS and soft RTS. Now, hard real time systems have got a stringent time constraint. The time constraint that is given is very stringent. Now, this stringent time constraint must be adhered to, must be respected. If this time constraint is violated, then violations will lead to catastrophes. For example, you have to land within, a plane has to land within maybe 1 minute. All right. Now, if it exceeds 1 minute, then it can crash. Take another example, say a nuclear power plant or some power plant, some thermal plant, where you find that the temperature has gone very high beyond the safety limit, and you have to start the coolant and put the power, shut off the plant within some specific time. And suppose your system that is controlling it is sluggish enough that it does not respect that time, it does the thing, but does it much later. By that time the situation has blown off, right. So, that is not allowed in hard real time systems. Why do we call it real time systems? Because these time constraints are specified in terms of real time. Real time means what? 1 second, 2 seconds. By this clock, this is a real time clock. Time is ticking. On the other hand, what is the other sort of time that we discuss about? We discuss about so many cycles. Suppose I say that the light must be switched off after 50 cycles. Vis-a-vis, I say that the light must be switched off within 1 second or 1 minute or 1 second. What is the difference? If the cycle clock is 50 hertz, then they are equivalent, because I have said after 50, right. So, it will be fine. But if the clock is slow, then 50 cycles will come after 2 minutes, right. So, that is the basic difference between real time systems and normal, I mean the typical computer systems that we talk of. On the other hand, hard real time, soft real time systems, if we violate the time constraint, then we the quality of service gets reduced, quality of service reduced, but no catastrophe happens. No catastrophe happens. Okay. Now, embedded systems can be real time systems or may not be real time systems. All right. It may be a real time system or may not be a real time system. Again, on the other hand, similarly, real time systems may be embedded. Usually, real time systems are embedded, but real time systems can also be, say, a server based system. Okay. So, these two are not equivalent, that all embedded systems should be real time systems. That should be kept in mind. Next, we will come to a slide that will give you an example of an embedded system here. So, this is an example of an embedded system. Which is a digital camera. It has been taken from the book Embedded System Design, a Unified Hardware Software Introduction by Frank Vahid and Guy Vergès. Okay. It is a Wiley publication. So, here you see typical digital camera. What do we have inside? Now, first of all, it is a single function. It is single function, it is only one function that is being done, that is photograph is taken and stored, right. It is tightly constrained. How? It is low cost, otherwise people will not buy it, low power, it is small, portable, must be portable and should be fast. Now, we do not call it real time system. If the picture is captured a little slow, no catastrophe will happen, right. It is reactive and real time. I will explain what is a reactive system and real time system, but it is a reactive system and real time only to a small extent, because if you take the image, it is a soft real time or hard real time? It is a soft real time, obviously, because if it is very slow, then probably you will not buy this, okay, but no catastrophe will happen. Now, what is there? You can see the lens which is capturing the world through a CCD, charge coupled device. There is an A to D converter which is converting it. There is a charge coupled device preprocessor. Then here you see one thing that I, in the slide that I was showing about the embedded system architecture, all through you can see there is a communication channel going on all through this, that I did not explicitly mention, but communication is another very important part of this entire embedded system ecosystem. So, here you see that through the bus they are communicating, all right. The CCD processor data is going everywhere, and there is a microcontroller, there is a JPEG codec which is doing the conversion and compression, and also there is a DMA controller, memory controller, bus interface. UART is a serial parallel to serial converter, okay, and there is an LCD control. So, there are so many components inside an embedded system besides the process. Now, you see how many processors do you see here? You can see a microcontroller as a processor here, you can see a CCD preprocessor, pixel coprocessor, here is another JPEG processor. Multiplier, you can say that this is not a processor, just a multiplier, but that is also doing some processing. So, there are so many processors communicating. Now, the key point is that some of these can be hardware, can be implemented in hardware, some of them can be implemented in software, all right. We will see this further. Next, so what are the design challenges? Before I come to the design challenges, let me make another system level classification. One is reactive systems versus transformational systems. Reactive systems are those which react to an event that occurs. For example, there is a system like a camera, it does not of itself work. Whenever you create an event, there is an input, and in that input you put a pulse, like suppose you are pressing the shutter, then only it starts working. Similarly, it could be that this is continuously it is keeping watch, it is active, another system, but whenever there is an alarm situation, then only it starts working, and immediately it sends the response. And usually such reactive systems, in many cases such reactive systems react to an event which is an urgent event, and therefore, in many cases they are real time systems. On the other hand, so these are working on external events. On the other side, there can be transformational system, for example, image processing systems. You get a set of images, you get an image and you process it. In image processing, you do a lot of things, you do noise removal, you do segmentation, right, and you do go on doing all these things, different activities that you do, right. Now, that you are taking a data, some data is coming in and that data is being transformed through stages, not in the event of any not in the event of some explicit event asking for service. Okay. Here, if we go to this diagram, you can find that there will be some reactive components also here and some will be transformational components. So, often the system is a mix of these. Okay. Now, embedded systems have got a number of design challenges. A major design challenge is the cost. Obviously, cost is a very important aspect. Now, the cost has got two components. One is the NRE cost. NRE cost means non-recurring engineering cost. Okay. You have to, we will have to incur some cost on that. So, here are what are the challenges. The challenges are mostly the challenges are optimizing on different aspects. Okay. One is the cost. I mean, how much time, how much money I will spend in order to do this development, and that is also dependent on the time. This is also dependent on how much time I will give, size of the device, the system, the power. Power will come back to power time and again. Power is a very, very important factor in embedded system design nowadays. The performance, and flexibility. Okay. What do I mean by performance? Performance means how in regard to time, how fast does it work. For example, and it can be latency, it can be throughput. What is the difference between these two? Latency means the time to take a task. Let me give an example. Suppose the camera that we just now saw takes 0.25 seconds to take a picture, right. Now, I have got a camera A, some camera A, therefore, can take 4 pictures per second, right, because I have designed it in such a way that it can take a picture within 0.25 seconds, process it, do everything. Now, so its throughput is also 4 pictures per second. Latency is 0.25. This is latency, and this is a throughput. Now, there can be another camera B which has got the same latency, but it can take 8 pictures per second. How is it possible? So, this is the throughput and this is the latency. I said that camera B has got the latency of camera B also has the latency of 0.25 seconds, right. So, the camera B takes a picture. In order to take a picture, it also requires 0.25 seconds, just as camera A did, but camera B had 2 threads running, 2 parallel processing. So, therefore, while one is being processed, it could be pipelined, one is being processed, another is being fetched. In that way, I can enhance the throughput, but the latency is same. I hope the differentiation between throughput and latency is clear. So, that is performance. The flexibility is a very another important thing, and if I bring a product which has got the flexibility of adapting to, suppose now I bring a phone which can work in 4G as well as 5G. Vis-a-vis, there is a phone which is coming in 4G or only in 5G. Now, there is a feature differentiation. My phone which I am bringing now can work in 4G and 5G versus your phone which works only in 5G. So, I have got a flexibility. By that, I can get a hand over the market. That is one. Another point is that if I have got the flexibility, I bring the product in the market, and then I find that there are some more demands coming up from the user. Can I adapt to those demands? If my system is flexible, I can add new features to the system and make it more flexible. Okay? So, these are some of the challenges that we have to face. Now, in order to complete the discussion today, we will go back to another very important issue. The design metrics are all these, the NRE cost and all those things. NRE cost you should try to bring down, power is another. Now, each of these constraints are competing among themselves, they are competing among themselves. Therefore, we have to always find an optimization, right. There is no unique solution. Now, let us look at this diagram. What I am talking of now, which is a very vital factor in embedded system design, is hardware, software trade-off. And that is why embedded system design also goes by the name, the task also goes by the name hardware, software co-design. Both of these things are designed hand in hand. Now, let us look at this picture. Here in the digital camera chip, we have got so many functions to achieve. Now, this CCD processor, preprocessor, I can map it to a hardware. The JPEG codec, I can map it to a hardware, or this JPEG codec had the option that I run a software code on the microcontroller for having the compression, right. So, I have got an option of doing this compression in hardware or in software. Similarly, the pixel coprocessor could be done in a software or could be done in a hardware. What is the advantage if I do it in a hardware? It will be faster. What is the disadvantage of doing it in the hardware? The cost, the area, it will become more, it will become heavy, all those factors will come into play. What is the advantage of making it in software? It will be flexible, I can tune it further, but what is the disadvantage of doing it in the software? It will be a little slower, and there will be of course, I will need a microcontroller, and power consumption. Power consumption will come, we will deal with that separately. Similarly, this but some of the things that, for example, there is a bus interface, that is hardware. So, some are fixed or assigned, destined to be hardware, some are destined to be software, but some can be implemented by either hardware or software, and the designer's challenge is to really decide on which one should be done in hardware and which one should be done in software. Okay. So, we will take it up from this point, we conclude today. Okay.